Hi, I'm Ben Zimmerman, and I'll be talking about how non-invasive vascular health measures predict white matter lesions in humans measured using an automated lesion mapping tool adapted here to be BIDS compatible. So using near-infrared light, it's possible to measure the amount of light that is absorbed at a detector after passing through the brain. And we can actually detect the heartbeat on a trial-by-trial basis. And the shape of these waves carries information about the health of the arteries. That's because arteries are naturally elastic when they're healthy, so they sort of expand when the blood moves through them. And when this happens, the shape of the pulse wave has separable components of the forward-moving wave that's coming from the heartbeat and the reflective wave that's pushing back from the periphery. So the arteries get stiffer with age, so they expand less, and this is reflected in these peakier pulse wave shapes. Previously, we found that a measure of arterial elasticity from the optical pulse measurements that we call the pulse relaxation function, or prefix, predicted the amount of white matter signal abnormalities, which is a measure of white matter degradation in the brain. These white matter degradations, in turn, have been shown to predict cognitive decline. And this prediction seemed also to be related to age, where in younger adults, there doesn't seem to be too much of a relationship between arterial elasticity and white matter abnormalities. But in older adults, there's this negative relationship between arterial elasticity and white matter degradation. In that work, white matter signal abnormalities were assessed using hypointensities from the T1 weighted image. So in the current work that I'll be presenting here, we wanted to extend and improve this analysis on a sample of participants aged 50 to 70, when age-related changes in arterial health are thought to begin to affect the brain. And to do this, we collected T2 flare images, which enhances the contrast of white matter lesions, and adapted an existing automated lesion mapping tool to separate periventricular and deep white matter lesions, which are thought to possibly represent distinct entities. So we adapted the lesion mapping tool to work directly with BIDS datasets as well, and produce an intuitive output. And so this tool is containerized and can be run with Docker with a simple command. And it has a number of parameters that are tunable that result in improved either sensitivity or specificity of the lesion identification. So these are some of the options. Some of these options depend on whether or not you already have common BIDS derivatives, such as fMRI prep run or FreeSurfer. And some of the parameters more directly influence the detection of the lesions themselves, including like the size of this ignored midline or the threshold for a white matter mask. At the simplest level, all that's required is a T2 flare image. And the program uses FSL tools for image processing. If you already have fMRI prep or FreeSurfer derivatives on your BIDS dataset, you can use those derivatives to improve the lesion mapping by improving brain extraction or using anatomical segmentation from FreeSurfer to guide lesion identification. The only caveat is that if you use FreeSurfer, then you need to share your FreeSurfer license directory to this specific location in the container. Lesion Mapper will output a summary HTML file with lesion volumes and some visualization. So here these orange highlighted sections are showing where Lesion Mapper has identified some lesions. But there's also nifty files of the actual lesion maps, as well as the transformations and intermediate files, which are output to a generated Lesion Mapper folder in the derivatives directory of the BIDS directory. So here, first we wanted to show that our results from the adapted version of Lesion Mapper don't diverge too substantially from the older published version that it's built on. That's this Wetter et al. 2016 paper. And in fact, we see a good correspondence using the older version of Lesion Mapper and the newer BIDS compatible version on our sample. Interestingly, when we separate the periventricular lesions from the deep white matter lesions, these two different types of lesion load do not seem to be very well correlated, which somewhat suggests that they may be different entities. In our sample, the total white matter lesion load significantly correlated with the average pulse pressure, which was measured on the arm outside of the MRI scanner. We also see a suggestive trend where higher values of our optical measure of arterial elasticity seems to predict lower white matter lesion loads. Data collection is ongoing. This is not significant now, but it will be interesting to see if this relationship holds up in the final sample of participants. In the future, we'll acquire a second time point on our sample to assess if vascular health predicts longitudinal changes in white matter lesions. And further, given that the periventricular and deep white matter lesions may represent partially independent processes, it will be interesting in the future to see if periventricular and deep white matter lesions are differentially related to physiology and cognition. Finally, since the application is BIDS compatible, we hope to make it available as a BIDS app eventually. So with that, I'll thank you for your attention. This is a thank you to my wonderful lab and collaborators shown here. And the red boxes are highlighting the other co-authors of this abstract. So thank you.